Okay, so most of the homework is asking you questions about dimensional consistency. And we talked about this briefly. The dimensional consistency is the idea that both sides of an equation have the same dimensions. An equation that has that property means it's dimensionally consistent. And I'm going to ask you a bunch of questions about whether some equations that we use in environmental science are dimensionally consistent or not. And the way that you're going to be able to answer that question is to show me the derivation where you take the equation I'm asking about, you plug in the dimensions for each of the variables, and then you simplify the dimensions algebraically to show me that the dimensions on the left side simplify to the same dimensions as the right side of the equation. So I want to work an example just to give you an idea of how to do this homework. In this case, we're going to talk about the Darcy Weisbach equation. The Darcy Weisbach equation is a hydraulic equation. It's an equation that tells you something about the influence on the friction of a channel on the depth of the water and the velocity of the water. So a given channel doesn't determine how much water is flowing in a stream, for example. That's determined by the watershed upstream of that point. What you need is an equation that will tell you, well, is it slow-moving deep water or is it fast-moving shallow water? That's what Darcy-Weisbach equation helps us with. So the variables in the Darcy-Weisbach equation are listed here. That U bar is the average velocity of the stream water. G is the acceleration due to gravity. R is the hydraulic radius. S is the slope of the water surface. And F is a dimensionless friction factor. Now, in order to do a dimensional analysis with this equation, we have to know what the dimensionality is of all the variables. So U is an average velocity. We talked about that in terms of the basic equations of Newtonian physics. A velocity, hopefully logically, is going to be a length per time. G is an acceleration due to gravity. Well, acceleration, we talked about that too. That's the change in velocity over time. So that's a length per time per time. Those times can be combined to give you length per time squared. R is a fairly unique to hydraulics variable, and it's defined as the area of the cross-sectional area of the channel divided by the wetted perimeter of the channel. The wetted perimeter of the channel is the length of a line drawn from one wetted edge to the other along the bed. So A, cross-sectional area, hopefully we've got the dimensions of that down now, that's length squared. P is the wetted perimeter, that's just a length. It's a very ununiformly shaped length because it's along the bed of the stream, but it's still just along the line, the given length of that line. So we can think of the hydraulic radius as length squared over length. S is the slope of the water surface, or sometimes what we call the energy slope. That's the vertical distance change over some horizontal distance in the water, in this case longitudinal distance along the channel. So a slope then is going to be a length per length. It's a length of elevation or vertical distance change over a length of a horizontal distance. And finally, that F is the friction factor, and it is a dimensionless number or simply a count. And it characterizes the effects of friction. So a higher F means there's more friction.